In this lecture, we're going to look at the effects of electronegativity on one of the most fundamental reactions in all of chemistry, and that's the acid-base reaction. So, getting into it, what we're looking at today is, or in this short video, is the identification of acidic hydrogen atoms. These are often called protons. And so you'll often hear me say protons moving around, proton shuffling, deprotonation, a lot of words that have the term proton in them without talking about like the nucleus of an atom or subatomic particles. And that's because the proton is P plus, and a hydrogen atom that is a cation are the same. So if you take the hydrogen atom and you remove an electron, you leave behind the only a subatomic particle, a proton. So an H plus or a proton, these things are the same. Okay, so let's get that off of I need to get that off my chest because, like I said, I'm going to be using that term proton synonymous with acidic hydrogens. So why do we look at acid-base reactions? So one thing to keep in mind is that hydrogen atoms are more likely to be lost or transferred in a reaction than any other atom. And in particular, we're looking at the hydrogen cation, so mostly H plus or the proton. Okay, now identifying or finding acidic hydrogens is very useful. So acidic hydrogens, let's just define this term first. So acidic hydrogens are H atoms that are most likely to be lost in an acid-base reaction. Okay, so these are of all of the hydrogen atoms, these are the ones that are most likely to be lost. Now, when I say all of the hydrogen atoms, I'm again thinking about chemistry in as an organic chemist, where I've got molecules that have multiple hydrogen atoms. Whereas in high school chemistry or what is the typical first-year chemistry sequence course, you might look at things like HCl, hydrochloric acid, where there's only one hydrogen atom. Here, we're gonna have multiple hydrogen atoms. It's useful to be able to identify which one is the acidic hydrogen. So I'm going to ask that question. Which one is the acidic hydrogen atom? And let's look at the bond line structure for a molecule called acetic acid. Now, you don't need to worry about the words acetic acid, definitely not at this point. That's more of an organic thing to think about. But this is a molecule. It's very common. It is the active ingredient in vinegar. So the more concentrated of vinegar that you have, the more bitter that stuff is, the more acetic acid it is. Acetic acid is an interesting term. It's not a very strong acid like we see in hydrochloric acid. It doesn't cause burning and that sort of thing. In fact, if it's diluted in water, it's very safe to consume, and we actually produce it quite a bit. It's a byproduct of alcohol consumption. So if people consume ethanol, the end product of ethanol consumption is acetic acid. Interestingly enough, the molecule between ethanol is that molecule that, while toxic, does cause a little bit of delirium, which people enjoy. There's a molecule in between ethanol and acetic acid called acetaldehyde. That molecule causes fatigue, dry mouth, light sensitivity, extreme dehydration, ultimately can kill you in high doses. But in low doses, it's just considered the hangover molecule. If we didn't have that molecule, there'd be no such thing as a hangover, which might be maybe more problematic. Anyway, so we have acetic acid. It's got this phrase acid in it. It's not the most strongest of acids, but it still has an acidic hydrogen atom. So which one is the acidic hydrogen atom? Back to the question at hand. It's the H atom attached to an electronegative atom. That's really helpful for us because in our molecules that we study as organic chemists, for the most part, we see a lot of hydrogens, but for the most part, they're bonded to carbon. So in cases where they're not bonded to carbon, that tells us right away that that's probably our acidic hydrogen. Okay, and so of the four H atoms, excuse me, this one is the acidic hydrogen. Why? Because if we look at all of the atoms that we have present, we've got carbon, hydrogen, oxygen. We said previously that carbon and hydrogen had very similar electronegativity values, so you won't see much of a dipole across those covalent bonds. But when hydrogen is attached to oxygen, there we can start to see a dipole. We would have a partial negative charge in the oxygen, partial positive charge on the hydrogen atom, and we could even draw our dipole arrow with a plus tail towards that hydrogen atom. So when acetic acid undergoes an acid-base reaction, it's most likely to lose that hydrogen as an acidic hydrogen. So that's it for this lecture. We're going to look a lot more at acidic or acid-base reactions with organic molecules in future lectures and even future labs. But for now, we're going to keep it just to let's find that acidic hydrogen within the molecule. And that'll be the only content we need to worry about in terms of acid-base reactions for exam 1.